In this chapter, we will extend the catenary curve definition to multiple connected curve network, to simulate a network of hanging chain model. You may open the Grasshopper file provided in the resource folder to follow along. Draw 5 curves on Rhino viewport, and reference them in Grasshopper using the curve container component. Ensure that the curves intersect each other. Let's connect these curves to the catenary curve definition from Chapter 3. Reset, and enable the solver. The resulting curves form a catenary arch under the influence of load, spring, and anchor goals. However, these curves are unconnected, and not influenced by forces acting on separate curves. To simulate a connected network behavior from these curves, we must first identify the intersection nodes, and shatter the curves into smaller curves, spanning between these nodes and endpoints. Use the Multiple Curves command under the Intersect tab to identify the intersection nodes. The outputs from Multiple Curve component of the intersection nodes is 3D points. Index A, B are the lists of indices that identify the parameters from param A and B associated with each curve. Read the output in a panel. For example, 0 from this list means that the corresponding value in param A list is the shattering parameter for the curve at index 0. Merge index A and B in a single list. Repeat the same for param A and B. Create a number series with count value equal to the number of input curves. Use a quality operator from Math tab, use the merged index list as first number, and grafted number series as input for second number. This will create a list with 5 branches of Boolean values. Each corresponds to a number from the number series. Use the dispatch list command to sort the list of merged parameters using the Boolean list. Resulting list A consists of 5 branches with parameters corresponding to its respecting input curve. Use the shatter command to split the input curves using this parameter list. Graft the curve input because the parameter list is branched as per individual curve. The resulting output is a list of split curves. Next step in this workflow is to divide these curves. Since these curves have different lengths, using the divide curve with a single count value creates segments of variable lengths. To minimize this variation, the count input must be varied for each curve based on its length. Let's assume that the length of each shattered line segment is 10 units. Divide the length of each curve by 10. Rounding of the result to the nearest ceiling value will give an integer value for count input. The curved divisions formed this way are of comparable length. Create a polyline between these points, and explode it to get a list of line segments. Replace all the inputs of catenary curve definition with the new set of discretized geometries. The list of line segments is the discretized geometry to be used as springs. List of points from vertices to be used as particles with load goal. And the endpoints from initial curves to be used as anchor points. Before using the points for load force, ensure there is no duplication of points in the list using Kangaroo remove duplicate points command. Flatten the points input. Reset, and enable the solver. The resulting curve is affected by the goals of connected nodes, and networks as well. Line segments' displacement is proportional to their distance from anchor points. We can also add goals to simulate what might happen with additional loads at intersection nodes. Let's add load at the intersection points. And the force vector acting in the opposite direction, that is, negative z direction. To make this goal more effective, scale this force vector by 20 times. Connect this goal to the goal merge component. Reset and enable the solver. We can see that the intersection nodes pull overall geometry towards negative z, whereas the load on remaining points pulls the curves in positive z direction. Once this workflow is set up, try changing the parameters to understand how different goals affect the simulation result. Try changing the input curves, and increasing their numbers. In the next chapter, we will learn about collision goals using Kangaroo library.